Okay, in this lesson, what we're talking about is the formal definition of a derivative. So the big question then, and probably the term that you've been hearing a lot as you've been taking calculus is, what is a derivative? Well, a derivative, very simply put, is just a collection of slopes of tangent lines for a function f. So given a function and you graph it, if you wanted to measure the slope at every point and then plot those new points on a graph, that would be your derivative. So what this allows us to do is it allows us to find instantaneous rates of change. So what you'll see are two graphs. One measures the average rate of change from a point to another point. The other measures the slope at a specific point, or the slope of a tangent line. And so that's kind of where we're going in this class, is how to find instantaneous rates of change using this idea called a derivative. So there's some notation that you're going to become more familiar with, and this is derivative notation. So the first one here, you'll see f, and it has a little apostrophe, and then your parentheses and x. So we say this f prime of x. So it's similar to the function f of x, except it's the function's derivative, f prime. If you see a y with a little dot above it, this was Newton's notation. So remember, Newton and Leibniz were the people that really founded and discovered calculus, and Newton denoted things with instantaneous rates of change as y with a dot above it. You'll also see, similar to f prime of x, you'll see y with an apostrophe, we would say y prime. And then the last one down here, this says the derivative of y with respect to x. So derivative of y with respect to x. And this was Leibniz's way of notating things. So the nice thing about dy dx is it's going to have a few more uses later on when we're talking about how to find derivatives implicitly, as well as whenever we're finding antiderivatives or integrals. The idea of dy dx is going to help us out a lot. So we're primarily, for today, going to use f prime of x or y prime, but don't forget about dy dx. This is going to be one of those things that we continue to use over and over and over again. So how to obtain a derivative then. So say we take a function f of x equals x squared, which is graphed here rather crudely, and you wanted to find the slope of the function at x equals 1. So we wanted to find f prime of 1, or the instantaneous rate of change at the x value x equals 1. Well, what I could do is I could take a point, another point on my graph that's really close to 1 but not equal to it. So I'll call it 1 plus a small change in x. And as I move this small change in x, and it gets smaller and smaller and smaller and smaller, the closer my line ends up to the point 1. So I'm going to get points like this, and then this, and they're going to get closer and closer and closer until I have exactly the slope of my tangent line. So this is how we obtain a derivative. We use a point, x, and then another point, x plus a small change in x. And what it's doing is it's taking the idea of average rate of change, f of b minus f of a over b minus a, and it's putting it on a really, really small scale to where a and b and f of a and f of b are so close together that they're indistinguishable. So the way that we do that mathematically is if we want to find the slope of a line, we're going to say that that change in x gets really, really, really close to 0. So we're going to make it so small that it's hardly measurable. And so what we have here is the definition of a derivative. It says the derivative f prime of x is equal to the limit as the change in x goes to 0 for our function f of x plus delta x minus f of x divided by delta x. And you'll notice that this looks really similar to f of b minus f of a over b minus a, where b is really just the point a plus a tiny, tiny change in x. And so if you think of it this way, this is really going to help you with the definition of a derivative. So let's look at an example. Given the function f of x equals x squared, let's find the derivative f prime of x. So what we need to do is set this up. We're going to say f prime of x equals the limit as delta x, or the change in x, goes to 0 for a function f of x plus delta x minus f of x divided by delta x. So what is f of x plus delta x? all this is we're taking our independent variable x and we're applying a translation, a horizontal translation just to the left by a value of delta x. So what I could do is replace my independent variable in my function x with x plus delta x, and then the piece that's squared still remains. And I know that f of x is just x squared. So whenever I put this together, f prime of x equals the limit as delta x goes to 0 for my function x plus delta x squared minus x squared divided by delta x. The nice thing here is I can use algebra to figure out the rest. So f prime of x equals the limit as delta x goes to 0. And I can expand my binomial here using, I could either FOIL or I could use Pascal's triangle or binomial theorem. However you want to do it, it's totally fine. But what you're going to get when you expand x plus delta x squared is x squared plus 2x times delta x plus delta x squared minus x squared divided by delta x. So the x squared stays, and then my expanded form of x plus delta x quantity squared is x squared plus 2x delta x plus delta x squared. What you'll notice now is that everything without a delta x is going to cancel. So x squared minus x squared is 0. So what I have is f prime of x equals the limit as delta x goes to 0 for 2x delta x plus delta x squared divided by delta x. What I can do at this point is I can factor out delta x from the numerator. So f prime of x equals the limit as delta x goes to 0 for delta x times 2x plus delta x divided by delta x. So all I'm doing is I'm taking out a delta x here and a delta x here. Whenever you multiply a number by its reciprocal, it becomes 1. So f prime of x then is equal to the limit as delta x goes to 0 for 2x plus delta x. So at this point, I still haven't actually found the limit. And the reason I haven't found the limit is because if I plugged 0 in for delta x in the beginning, I would get an indeterminate form. And what we know about indeterminate forms is that you either need to factor or use the conjugate in order to get rid of that indeterminate form. So what I can do now is I can simply plug in 0 for delta x, and that's going to give me my value. So the limit as delta x goes to 0 for 2x plus delta x equals 2x plus 0. So I'm taking the value that delta x is approaching and I'm plugging it in for delta x. What this gives me then is 2x. So my derivative f prime of x is equal to 2x. If you were to graph this on a graph, you'd have your function that you started with, x squared, and then you're going to have your derivative graph, which looks like this. And what the derivative is going to do is it's going to take all of the slopes of all of the tangent lines for the function f and then plot them. So using the same x values, it's going to plot the x value and then the slope. So the cool thing here is we go from a quadratic to a linear.